Is it possible that living brains can someday power our computers? That provocative question isn't just fuel for sci-fi anymore. It's rapidly becoming a reality. Researchers are growing miniature brain-like structures, or organoids, in laboratory dishes, linking them to digital systems and watching them learn. It's captivating, controversial, and just the beginning. But here's where it gets truly groundbreaking. These dish-grown brains are already performing simple tasks, opening vast new possibilities in both computing and biology. Let's step into the lab. Back in the 1960s, Star Trek's Captain Kirk once encountered a dramatic bowl filled with interlinked brains running an advanced computer. What once seemed pure fantasy is now inching towards fact. Professor Thomas Hartung at Johns Hopkins University even points to this scene, reflecting on how yesterday's science fiction is today's research focus. In the past few years, advances in organoid computing have made the blending of living neural networks and silicon a reality. Back in 2022, Australian scientists at Cortical Labs managed to teach their so-called dish brain to play Pong, the iconic computer game. Hot on their heels, researchers in China developed the Metabot platform, where human brain cells maneuver robots. And companies such as Swiss-based Final Spark and Cortical Labs are unveiling plug-and-play brain computing hardware for sale or remote use. Meanwhile, at leading universities and institutes around the world, including Johns Hopkins, work is underway not just on the tech, but also on the ethics. How do we responsibly experiment with and teach these living computers? What new communication tools and frameworks do we need? And this is the part most people miss. The conversation is as much about philosophy as technology. Why are these new biocomputers so exciting to scientists? Imagine drug researchers being able to ask an organoid computer how a potential Alzheimer's medication actually feels to a cluster of real human neurons. Something impossible with traditional computer simulations. In addition, brain-based computers might eventually offer huge boosts in efficiency, handling complex or uncertain data in ways even the world's fastest supercomputers can't. Human brains perform intricate parallel processing, solving difficult problems with remarkable energy thrift, a mere fraction of the power that digital machines require to approximate similar tasks. To mimic even a tiny bit of brain activity takes supercomputers more time and 1,000,000 times more energy. The upshot? True organoid computers could leave traditional silicon far behind in certain areas. Dr. Catherine Ball, a futurist and author, sums up the promise boldly. Human neurons always outperform silicon. So, it makes perfect sense to use the most advanced form of cognition, the human brain, even in miniaturized form. But biological computing hasn't arisen in a vacuum. Professor David Gracias at Johns Hopkins, one of dozens of specialists advancing the field, points out the convergence of several key technologies. New culture methods that keep cells alive for months, AI tools to make sense of the explosion of experimental data, and advanced micro-wiring systems that connect digital interfaces to living organoids. Reflecting on his own work, Gracias asks the obvious question. Instead of laboriously mimicking the brain in silicon, why not just use real brain tissue? Currently, the organoids Gracias works with may contain around 10,000 human brain cells, forming a tiny sphere 0.5 millimeter across. This may sound minuscule, but keeping these clusters alive and healthy is a technical marvel. Without blood vessels, organoids can only grow to a few hundred microns. Otherwise, their cores begin to die. Hence, a race is on to develop ways of nourishing larger brain clusters, including engineering artificial blood vessels. Another major challenge is connectivity. These organoids are wetware, living tissue kept alive in nutrient-rich fluids. Electronics and liquids don't mix easily. Water can short out computer circuits. Gracia sees this necessity as a paradigm shift. We need to design computers that operate with living moist matter at their hearts. Attaching digital components to these tiny brains is tricky. Simple, two-dimensional organoids can be linked to electrodes with relative ease. To capture the dynamic interactions in a real brain, though, three-dimensional organoids are required. But placing a complex, living sphere on a flat interface leaves most neurons unreachable. Gracia's team, inspired by EEG skullcaps that monitor brain activity, developed a miniature version, a delicate shell that wraps around a 3D organoid and records activity from many angles. He even teases future advances like electronic tattoos or wireless sensors, which could replace the tangle of wires, possibly by using light or other non-contact technologies. But here's something to ponder. Even if we can record signals, do we understand them? The brain communicates in a language of chemicals and electrical impulses, Gracias notes. Scientists have to painstakingly discern this language, sending endless waves of signals into the organoids, then tracking their responses. Decoding and interpreting these reactions may be as complex as translating between totally foreign languages. And this produces huge volumes of data, necessitating skilled data scientists to keep up. Training an organoid computer, Gracias says, is chillingly similar to teaching a toddler. Through patterns of encouragement, rewards such as electrical or chemical signals, and discouragement, researchers try to coax the brain to repeat preferred responses. Some experiments even involve giving the organoids dopamine, a natural reward neurochemical. Recent efforts have focused on multimodal shells that can both record and stimulate the brain chemically and electrically. Commercialization is racing ahead. Following the success of the Pong-playing dish brain, Dr. Brett Kagan and the Cortical Labs team shifted from academic research to developing commercially available organoid computing platforms. Their product resembles a server rack, 40 brain computers joined by 60 digital contact points each. The cell cultures have a limited lifespan, about 6 months, but institutions will soon be able to purchase single units or entire racks, or access them via the cloud. Already, labs across the world are connecting remotely to Cortical Labs computing units for research. Kagan stresses the importance of broad collaboration and accessibility, likening their business model to selling the picks and shovels in a gold rush. When off-the-shelf tools fell short, Cortical Labs spent over a year building custom environments, and can now help others build new test systems vastly faster than before. One intriguing focus is analyzing not just the presence or absence of neural signals, but their specific shapes, like musical notes, not just drum beats. Exploring both 2D and 3D organoids, the company finds that 2D models offer more control and scalability for tasks that don't require the complexity or attendant ethical challenges of full brain-like 3D structures. Kagan even asks, why jump straight to human intelligence when bee or worm brains might be more than enough for many uses? This provocative perspective could stir debate. Should we pursue maximum sophistication or focus on practical, ethical, and manageable systems first? Final Spark, the Swiss company led by Dr. Fred Jordan, also offers remote access.